Hi. All right, part 4. I believe this will be our final part for exponential and logarithmic functions, and that is to use both of these concepts to solve equations. So there are 3 methods when the variable's in the exponent to solve an equation, and the first method is when you make the bases the same. Now, I gave you an example in the very first PowerPoint of 2x equals 5, and I say, how do you figure out what x is? You can't use method 1. You can't make 5 2 to some power. We don't know what that power could be. So we could use 2 different methods to do this. I'm going to just use this very simple example. We can rewrite it using our definition of a logarithm. So I unwrap my equation. So I start at the exponent and I say x equals log base 2 of 5. Now this is my exact value. Exact. Because log base 2 of 5 is going to be an irrational number. So what if I want the approximate value? I have to type it in my calculator. And you might remember I can't type this in my calculator without first doing the change of base. So let's look at method 3. Method 3 is the one that is most commonly used to solve exponentials because it is, you don't have to worry about change of base, and it works all the time just about. So what we want to do is we want to take the log or natural log of both sides of the equation and then simplify using laws of logs if you have to. So let's start out with this first one, 2 to the x equals 5. I just write log in front of everything on the left-hand side and log in front of everything on the right-hand side. And what do I do here? Well, I know from my rule with from part 3 that if I have an exponent for a log, I can just move it to the front. So I get x log 2 is equal to the log of 5. Now I want to get the x all by itself. It's x times log 2. So I'm going to divide both sides of my equation by the log of 2, this whole thing, to get the x all by itself. So that gives me x equals log of 5 divided by log of 2. This is also an exact solution. Now, it might look different than this one up here, log base 2 of 5, but actually they are the same, because if I were to apply the change of base formula to log base 2 of 5, I would get log of 5 over log of 2. So let's type it in our calculator and find out the approximate solution. Okay, so I'm going to take the log of 5, close parentheses, divide it by the log of 2, close parentheses, and I get this number, 2.321928095. That is an irrational number, keeps going forever. Read Alex very carefully. It tells you the specific number of decimal points to round. So I'm going to round to, I'll just go 2 decimal places, so 2.32. So this is approximately equal to 2.32, and that is my approximate solution. Now, again, read carefully in the problem if they want an approximate or an exact solution. If I want approximate, I will tell you how many decimal points I expect you to round it to. So 2 to the x equals 5. X is about 2.32. So let's do a couple trickier examples. What if I have 10 to the 3x equals 5? So I'm going to draw a line over here, maybe, and I'm going to do it right here. So again, you can choose your method. If I rewrite it using the definition of logs, I unwrap, starting at the exponent. So I have 3x equals log base 10 of 5. Now log base 10 of 5, that's a common log, so I don't have to worry about change of base. And then I'm going to divide both sides by 3 to get x all by itself. So I get x equals log of 5 divided by 3. Now again, this is my exact I want my approximate, I need to type it in my calculator. Do not move the 3 inside the log. Just like you wouldn't move a number outside a square root into a square root, the same thing applies here. So when we put it into our calculator, log of 5 divided by 3, I make sure I close parentheses, and then I divide by 3. So 0.23299. So let's go to 3 decimal places this time. Since it's a 9 next to the third spot, I'm going to round up. So 0.233 is the correct number. So this is approximately equal to 0.233. That's the first example. That one's really straightforward. The second one, you cannot use method 1. There's no way we could make these have the same base. You cannot use method 2. You can't use the definition of logs to undo this stuff. Well, you can, but it's more complicated. Sorry, you can, it's just more complicated. This one, by far the easiest method is method 3, taking the log of both sides. So let's go ahead and do that here. So I take a log of the left-hand side, 5 to the x plus 1, and that's equal to log of the right-hand side, 6 to the 2x. Now, for both of these, I'm going to move the x's to the front. So I move the x plus 1 to the front, and that's log of 5. There are a lot of 5's in this. And then I move the 2x to the front, and that's log 6. Now I have a problem. Let me show you my problem with red. So the problem I have is that I have x here, and I have x here, and I want to make it x equals. I want a single x. So you might have done this some when you were solving formulas for a variable. I'm going to go through the steps here so you can see how to do it in this case. And this does actually come up relatively frequently in these kinds of problems. First thing I'm going to do is I need to get rid of the parentheses here. I could divide by log 5, or I could distribute. I'm going to distribute, so I have x times log 5 plus 1 times log 5. And that equals 2x times log 6. Now I want all the x's on one side, so I'm going to take this term and I'm going to subtract it and put it on the other side. So I subtract x log 5 from both sides. Keep accidentally pushing a button there. Minus x log 5. Now, these are not like terms. I cannot subtract them. So I cannot do anything except write them next to each other. So I'm going to do that. Let me make this line a little longer here. So I have the left-hand side is just log 5 because these canceled. And the right-hand side, I have 2x log 6 minus x log 5. How do I make it so it has a single x? Thinking. I have an x here. I have an x here. The only way I can make it a single x is if I factor the x out. X. What's left? Painting with colors. This just gives you time to think. So I divide the x out of the first term. I have everything that's left. 2 log 6. I divide the x out of the second term. I have log 5. And that equals log 5. Now I can get the x all by itself because there's only one of them. So anytime your variable shows up more than once in the equation, you must get all of those instances with that variable on one side and factor it out. So finally I'm going to divide both sides of the equation by 2 log 6 minus log 5. So I get x equals log of 5 divided by 2 log 6 minus log 5. That is the exact solution, and we're going to leave it at that. All right, I'm not going to cover both of these examples because we're already 10 minutes into this. These equations can take a while to solve, as you can see. The important thing to remember is that you must first isolate the exponent before you use one of the three methods discussed on the previous slide. So on this equation, I would first add 29 to both sides, and so I would have the 10 to the x all by itself. So I'd have 10 to the x equals 60, 80. And then I would use one of those three methods. For this one, you might say, oh, it is all by itself, but it isn't because I have this coefficient of a 2 in front. So I would first divide both sides by 2 to get the exponent all by itself. So I'd have e to the x plus 5 equals 5 halves. Once I have it in this form, then I could use one of those first three methods to solve. All right, so now what happens if I have a log equation and I have the variable trapped in the argument of the log equation? So what if I don't know this? The only way for you to solve this kind of problem is to convert it to an exponential. So you must convert. Now remember, if it's a natural log, I've lost my pointer, if it's a natural log, it has a base of e. So when we're converting a natural log x, we change it to e to the y equals x. Always put yourself a little magic e in there and then do your loop. Okay? So now the rule for isolating still applies. I need this all by itself before I can convert it. So I'm going to add 5 to both sides first. And so I get negative 4 natural log of x plus 1 equals 12. Then I'm going to divide both sides by negative 4. Divide by negative 4. And so then I get the natural log of x plus 1 is equal to negative 3. Now, this can be negative because, remember, logs give us powers, and powers can be anything we want. So now I'm going to convert it. So I say e to the negative 3 is equal to x plus 1. So I subtract 1 from both sides, and I have x equals e to the negative 3 minus 1. Now, this is exact, except we never, ever leave a negative exponent in an answer, so I have to change e to the negative 3 to a positive exponent. So x is actually 1 over e cubed minus 1. This is the answer that you would enter into ALEKS. If you wrote negative 3, actually they'd probably make you give the approximate answer, but if you wrote e to the negative 3, that's not right. So there's lots of examples online of exponential growth and decay. Radiocarbon dating is an excellent example of exponential decay. And if you go on YouTube, there's some great videos you can watch that explain what radiocarbon dating is, and it helps you kind of understand the word problems better when you see them here and in ALEKS. Exponential growth, a really great example, is compound interest. So I'm going to do just two examples for you, one that is exponential decay and one that is exponential growth. So if we look at both of these use the same formula, and that is a equals p e to the RT. Now e is our little letter e I don't know if I've explained that in here. It's a number. Goodness gracious. So e is a number. It's about 2.7. And so anytime you see e, it's not a variable, it's a number. It shows up on your calculator, and in fact, if you go to your calculator and type the letter e on the TI-84, it's above the division symbol. If you're raising it to the power, it's above the ln symbol. But so if you just type e, enter, it tells you how much it equals. Just like pi is about 3.14, e is about 2.718. So it's a number, and Wikipedia has a great explanation of what the letter E is. If you just search, you could search for exponential or natural number or Euler number, E-U-L-E-R, and you should find it. Okay, so this formula, A is the amount at the end, P is the amount at the start, the initial amount, the amount invested. R is the rate, and if they tell you that the rate, it's an exponential growth, you're going to make the rate a positive number. If they tell you it's an exponential decay, you're going to make the rate a negative number. So I'll show you how to do that for the decay here. T is the number of years. So the mass of a radioactive substance follows an exponential decay model, and with a decay rate of 2% per day, find the half-life of this substance. So half-life, by definition, is the time it takes for us to have half of the original amount. So if you think of something like radioactive waste from a nuclear power plant, the elements in the radioactive elements in the waste have a half-life. You might hear people talk about that, a half-life of 500 years or something. And what that means in 500 years, it will only half of it will exist there anymore. The other half will have broken apart and not be radioactive. But that's part of the problem with nuclear waste, is that it has very long half-life, which means it doesn't take us that long to create it, but it takes a long time for it to decay on its own. So here's a radioactive substance with a decay rate of 2% per day, and I want to know how much time until we have half the original amount. So if I have an original amount of P, the amount at the end is half P. So I would write 1/2 P is equal to P E. Now my rate is 0.02, but it's negative because it's delay. Because it's decay. So negative 0.02 T. And then I have to solve this equation for T. Now remember, the first step is to get the E part all by itself. So I have to divide both sides by P. And this really works out because I have no idea what P is. It's just some number that I don't know that I start with. But P divided by P cancels out. So I get 1/2 equals e to the negative 0.02 t. Now I can take the natural log of both sides of my equation. Natural log of 1/2 equals natural log of e to the negative 0.02 t. So I move the exponent to the front. I have the natural log of 1/2 is equal to negative 0.02 t times the natural log of e. The natural log of e, everybody, is 1. So this ends up being the natural log of 1/2 is equal to negative 0.02 t. Divide both sides by negative 0.02 to get my answer. T is equal to natural log of 1/2 divided by negative 0.02. Now, that is our exact answer. This is a word problem. Never leave your answer in exact form in a word problem. So I need to calculate it. Natural log of 1/2 divided by negative 0.02. 34.657 days. It's about 34.7 days is the half-life. So that means if I have some radioactive substance in a barrel, every 35 days it would be half of the radioactive component of it would be gone. It would not be radioactive. This gets into chemistry. So you can go and do all sorts of research about that if you're interested in it. It's an interesting process. All right, so the next one is interest compounded continuously. Continuously means, so we compound interest yearly, quarterly, monthly, daily, and this is just continuously. And you would think that would be just a really giant number, but it isn't. It actually turns out that it's not that much different than having interest being compounded daily. It's an exponential growth model, and it follows the same formula as the decay model, but the R is positive. So I have money, I placed it into an account. at an interest rate of 1%, compounded continuously. After 2 years, there's $1,714.14 in the account. I want to know the initial amount placed in it. So now here, again, this might be a credit card. Credit cards have continuous compounding. So I want to know how much money was in my credit card, but who has a credit card with 1% interest? Okay, so anyway, after 2 years, the final amount in the account. So that's the amount at the end. So that's the A. 1714.14 equals P is what I don't know. E, my interest rate is 1% per year. It's growth, so it's positive, 0.01. And the time is 2 years. So I need to figure out what P is. I'm going to divide both sides by the e raised to that power. So this is a simple substitution problem. It's not nearly as complicated as the previous one. 1714.14 divided by e, 0.01 times 2 is 0.02, so e raised to the 0.02. Okay, so I type in 1714.14 divided by e to the power, so second natural log gives me e to the power 0.02, $1,680.20. Always round to the nearest penny in money problems. 1680 and 20 cents. So the original money I had in the account was $1,680.20. That's it. That's all my examples. That's the end of everything that I have for you on exponential and logarithmic functions. There's much more that you could learn and we could cover on this topic. So if you have any questions, please ask me. At this point, you should have everything you need to do to go into the ALEX and do the homework for Project 4, Part 1. Good luck, and thanks for watching.